The first scientists to identify alpha particles by a direct method were Rutherford and Royds. They knew that radium-226 decays by alpha emission to form a nuclide known as radon. So write down the equation. Well, hey, hopefully we can all do this, right? Okay, so on this side we've got 226. Is that 88? Yeah. And that's our radon, right? And then that turns into, radium, right? That decays into radon. So figure out what these numbers are. Remember that the alpha particle is a 4-2. So figure these numbers out, and that's what the two marks are for this guy and this guy, right? Okay. You know how to balance that equation, right? I hope you do. I'm so fearful. You might get out in the world and not be able to balance a nuclear equation. All right. So and then what they do is they stick this sample inside this large closed cylinder, right? And they let it sit for 6 days. And what's going to happen here is that these alpha particles are going to come out, and they're able to go through this little barrier, and they'll go into this cylinder here, and they'll become helium gas, basically, right? That's what's happening here. They put 6.2 times 10 to the minus fourth moles of pure radium-226 in a small closed cylinder. Cylinder A is fixed in the center of a large closed cylinder. The experiment lasts for 6 days. Deduced that the activity of the radium-226 is almost constant during the experiment, right? Well, look how small that decay probability is, right? You've got a crap ton of like 6.2 times 10 to the minus fourth moles is a lot of atoms, right? As we'll figure out in a moment here. But the decay probability is so small, really, that it's going to stay constant. But we can show this. Let's show it. Okay. So what I'm going to do is I'm going to show, I'm going to use this, right, that the activity is the original activity, e to the minus lambda t, which this is not in the data packet, right? I'll tell you that much. But it's but anything that scales with the number, this is in the data packet, right? N is n naught e to the minus lambda t. But since activity is just lambda times n, then we can get there very quickly with this, right? So this is going to decay like this. So the question is, if this is, say, 100%, right? Let's say it's 100%, right? And then just go e to the minus lambda, plug this lambda in, right? And then t is 6 days. Notice that that's seconds to the minus 1, so put 6 times 24 times 3,600. 6 days times 24 hours per day times 3,600 seconds, right? So plug this in for that. Plug that in for t. Solve for what percent you have left, right? and you'll get, I got like that it was 0.99 or 99.99927%, right? So it's nearly constant. The change is 1 part in 100,000, yeah. Okay, so it's relatively constant. Okay, just do some calculation like that. Show that this number right there is really small, or is almost the same, right? Okay. Show that about 3 times 10 to the 15th alpha particles are emitted by the radium-226 in these 6 days, right? Well, now that we've established that the activity is constant, right, we're going to just figure out that our activity is lambda times n. So what is n? N is the number of moles times Avogadro's number, right? So look up Avogadro's number, 6.02 times 10 to the 23rd. Number of moles is this. That's our n, right? Okay. And you'll get that it's about 3.73 times 10 to the 20th atoms, right? Then plug that in, plug this in for your activity, right? And you'll get the decays per second, and it's about 5.2 billion decays per second, right? Remember, you've got a lot of atoms, though, right? 5.2 billion compared to 3.7 times 10 to the 20th atoms is vanishingly small, right? Okay. And then to figure out the decay, so step one is n is the number of moles times Avogadro's number, right? Step 2, activity is lambda n. So n is what you just figured out, right? Lambda is this, right? That's so many counts per second, right? And then to figure out the total number of decays, you're just going to multiply the activity times, they said 6 days, so 6 times. That's counts per second, 24 times 3,600, right? So this is just basically just multiply stuff, right? Okay. Number of moles by Avogadro's number to get number of particles. Number of particles times decay probability to get the number of decays per second, which is about 5.2 billion decays per second, right? And then multiply that 5.2 billion by this, and you'll get something that is about 2.7 times 10 to the 15th, not quite 3 times 10 to the 15th, okay? I got 2.7088 times 10 to the 15th decays in 6 days, right? All right. At the start of the experiment, all air was removed from cylinder B. The alpha particles combined with electrons as they moved through the wall of the cylinder to form helium gas in cylinder B. The wall of cylinder A is made from glass. Outline why this glass wall had to be very thin. And the answer to that is that alpha particles, you can stop alpha particles with a few inches of air or a sheet of paper. So they don't, since they're massive and ionized, that they tend to interact pretty strongly with matter, and they'll just become helium. Okay. Okay. The experiment was carried out at a temperature of 18 degrees Celsius, right? So that's our temperature, right, is 18 plus 273.15, right? Cylinder B, the volume of cylinder B was 1.3 times 10 to the 5th cubic meters, so our volume is 1.3 times 10 to the minus 5th cubic meters. The volume of cylinder A was negligible, right? So that we don't have to subtract the volume of that inner cylinder, right? Calculate the pressure that was collected. Okay, so then our number of moles will be the answer to the last question. B, letter I, right? The answer to BII, which was, for me, was 2.7088 times 10 to the 15th divided by Avogadro's number, right? Okay. So I got like 4.5 times nanomoles, 4.499 times 10 to the minus 9th moles, right? And then just plug this into PV equals nRT, right? So we've got our temperature, got to turn it into kelvins, right? We got our volume, we've got our number of moles, we've got R, so we can solve that. And I get less than 1 Pascal, which is really, really small. That's a very, very small pressure. All right. Less than 1 Pascal, but more than 0.5 Pascal, I'll tell you that much. All right, what do we got here? Rutherford and Royds identified helium gas in cylinder B by observing its emission spectrum. Outline with reference to atomic energy levels how an emission spectrum is formed. Well, hopefully you know this, right? So here's the nucleus, here's our orbitals, right? And the photons are made as they make jumps to make transitions downward from upper orbitals to closer orbitals, right? They release photons like that. So talk about how these orbits are well-defined stationary states. There don't exist states in between. That the electron goes from here to here in a quantum jump. It emits these energy levels that correspond to the energy differences in the orbits, right? Their work was first reported in a peer-reviewed scientific journal. So peer review means that other scientists in the field check over the work, and typically they'll offer suggestions, and if somebody is trying to publish something like a creationist article or something like that, they'll say, well, you know what, science has moved on from that. But basically, peer review basically guarantees they're looking for the validity of the work. Also means that readers have confidence in the validity of the work. So this is what by the way, we need with our news, right? All of our news sources need to have more peer review. Right now, we've got, anybody can say anything on internet, and people, people are prone to believe what they see. But anyway, there you go.